Hello everyone, welcome to Engineering Archives. This video we are going to look at learning problem number 4 for this chapter, dot products. So this problem says, determine the magnitude of the components of the force acting parallel and perpendicular to the axis of the pole. In the book, this question does not say the magnitude of, but what they mean is the magnitude, even though they don't use the words magnitude. And this is one of the problems with the questions in the book, that sometimes they're asking for something but the wordings are not appropriate. Okay, so but what they mean is they want to find the magnitude, and it is crucial to use the word magnitude in order to convey the right meaning to the students. And I faced a lot of problem with questions like these because I always try to find the thing that they asked for, and what they meant was something different. So anyway, basically we have to find the magnitude. Okay, so this is our force vector F, and they want us to find the magnitude of the two components for this force vector. One of those components needs to be parallel to the pole, okay, and this is the pole. This is the line OA, and this line is going to act as, you can consider this as an axis, okay. So if I extend this line on the pole, they want one component for this force F to be parallel to the pole, okay, so this is going to be one component, and they want the other component to be perpendicular to the pole. So the other component would be something like this. It would be drawn at right angle to the axis of the pole. Okay, so this is going to be the second component. Alright, so let me redraw this right angle triangle here in order to make it more clear. This is our force F, while this is the component parallel to the axis of the pole. Let's call this FP, and this is the component perpendicular to the axis of the pole. Okay, and let's call this component F per. And they want us to find the magnitude. Okay, so let's put the lines of magnitude here. These lines are just to denote that what we are finding is not a vector but just the magnitude of the vector. Okay, alright, so we know that when it comes to finding the components of a force, we use the third formula that we discussed, the third formula or the fourth formula, right? And since in this case they haven't given us the angle theta, we will again be using the fourth formula. So let's write down the fourth formula in our solution. So the formula is the magnitude of the component of the force F in direction of the pole line is equal to the force vector dot producted with unit vector in direction of the pole. Okay, so in order to find this magnitude, we need the force vector and we need the unit vector in direction of the pole. So let's start by finding the force vector F. So to find the force vector F, we can just use the angles that they have given us in this diagram. Okay, for the force vector they haven't given us the length measurements. There are some length measurements, but those length measurements are only related to the pole, as you can see. So we can find the unit vector using these length measurements, but we can't find the force vector using those length measurements. But we can use the angles that they have given us to find the force vector. So let's do that. And you should know that whenever they give us the angles, we don't need to go through the whole procedure of finding the length vector first and then converting that into its unit vector and finally converting that into the force vector. When we have the angles, we can directly apply the trigonometric identities to get the xyz components for the Cartesian form. So let's get started. So the x component is going to be 600 cos of 60. Taking the cos gives us the component along this line, and then taking sine of 30 would give us the component along the x-axis. But notice that this component is towards the negative x-axis, which means it is going to be negative. And let's put an I at the end. The y component is going to be 600 cos of 60 cos of 30. This time, this is the component that we get. And finally, the last component is 600 sine of 60, right? And doing that gives us the component along the z-axis. Let's put a k at the sorry about that. Let's put a k here and a j here. Okay. So now we have our force vector. So let us replace these identities with the with their respective numbers. So we have negative 150i plus 259.8j plus 519.6k. Now that we have our force vector, we can move on to find the unit vector in direction of the pole. So to do that, we first need to find the length vector r in direction of the pole. Okay, so for this pole, we can see that this vector, length vector, travels negative 4 feet in the x direction, 4 feet in the y direction, and 2 feet in the z direction. We can convert this into its unit vector by dividing it by its magnitude. Right? And we get negative 4 by 6i plus 4 by 6j plus 2 by 6k. So now we have our unit vector in direction of the pole as well. So we can move on to find the magnitude of the component parallel to the axis of the pole. By taking the dot product of the force vector with the unit vector. There's a k at the end here. Sorry about that. Okay. So multiplying the respective x, y, and z components, we get negative 150 times negative 4 by 6 plus 259.8 times positive 4 by 6 plus 519.6 times 2 by 6. And once we add them up, we come up with the number 446 pounds. So this is the magnitude of the component for the force F parallel to the axis of the pole. Now that we have our first component, we can move on to find the perpendicular component. So we can find the perpendicular component by just using the Pythagoras theorem. I'm not sure if we spell Pythagoras like this, but anyway. So the Pythagorean theorem says that the hypotenuse squared is equal to the adjacent squared and the opposite squared. So the adjacent is the parallel component, right? And the opposite is the perpendicular component. Substituting in the values, and isolating f perpendicular, or the perpendicular component, we get the value 600 squared plus, oops, 446, actually, no. So we subtract 446 squared from both sides, and then take the under root, and we end up with the perpendicular component equal to 401 pounds. Okay, so this was the procedure to find the magnitude of the components of the force parallel and perpendicular to the axis of the pole. We first applied the fourth formula, and then we used the Pythagoras theorem. Okay, thank you very much. See you in the next video.